is sponsored by the ICCE Center for Critical Intelligence Studies at Rutgers. So first, I want the director of the center, Ava Majlesi, I hope I said the right name right, to give an introduction to the center and the program and everything. Ava, please.
Thank you so much. Good afternoon, everyone. My name is Ava Majlesi, and I oversee the Rutgers Intelligence Community Center for Academic Excellence, otherwise known as the ICCAE program. It's a consortium that includes faculty and students from Rutgers University, City College of New York, Borough of Manhattan Community College, and New Jersey City University. Welcome and thank you for joining us for our series on artificial intelligence for intelligence analysis, hosted by City College of New York. The aim of this series is to make connections between technologies and applications and to enhance awareness of the importance of artificial intelligence in a national security context. The speakers in this series are active researchers and practitioners in using AI, data analytics, and machine learning techniques in defense, intelligence, and security applications. Before we get started, I would really like to thank the Office of the Director of National Intelligence for supporting our students through the ICCAE program. The federal government provides grants to public universities to enhance the recruitment and retention of a diverse intelligence community workforce with capabilities that are critical to the national security interests of the United States. You might be asking yourself why we are focusing on artificial intelligence if our goal is to inspire students to pursue careers in the federal intelligence community. Well, the fact is that advances in AI are going to have several impacts on national security, and that's in three key areas: the success of military operations, the robustness and accuracy of intelligence gathering, and also economic superiority. So the IC has an interest in a future workforce with diverse academic backgrounds, and that includes a workforce with advanced technology skills. And I would argue that not only does the IC need a workforce with the appropriate technical skills to advance these areas, but it needs a workforce capable of analyzing and addressing the policy implications and the unintended consequences of reliance on these emerging technologies. And so that is where all of you come in. I encourage all of our student participants today to become more involved in our program. We have a wide variety of professional development opportunities available to help propel you into intelligence careers. And you can learn more about our programs by visiting our website. It's intel.rutgers.edu. I will drop that into the chat in a moment. But again, I just want to thank you for joining us today. I hope you find today's session informative and helpful. And now I'm going to turn it back over to my colleague, Dr. Ju from CCNY, and he is going to introduce today's speaker, Dr. Rakesh Kumar.
Great.
Thank you.
Thank you, Ava. So because the format of the talk is a unique format, we are going to have an hour, maybe more, a little bit more than an hour, more or less. So the first part will be a career talk. The first part will be the technical application content, as usual. And finally, we are going to have a Q&A session. So I'm going to let the speaker to introduce himself, but I just want to say one thing. Teddy is actually the person, one of the major reasons to get me to do my postdoc research at UMass, Amherst, University of Massachusetts at Amherst, the Vision Lab there. He graduated there. I didn't see him, but I saw his paper when I was far, far away from this country. So I got here. I really enjoy working on the topic. And I also have a number of interactions with Teddy for a workshop in 2001 or 2003, right? Back there. And then I also visited him for my sabbatical leave for 1 year, basically stay in his lab for a year every week. So I really enjoyed that experience. So he's the vice president of information and computer sciences at SRI International. and also the director of the Center for Vision Technologies here in Princeton area. So before we start, I just want to say two reminders. First is that this whole session is recorded. It's going to be posted online in YouTube properly, so you can watch it later if you get in late, right? So we have like more than 100 registrations, so we can only allow 100 people. The second thing is that for question answering, to be more effective, efficient, I'm going to ask you guys to submit your questions in the chat box. Just put in the chat a very quick question there. I'm going to compile it, and then our moderator today is our star student, Jin Chen, is going to do the moderator, present the question to Teddy, and he answers the questions. So we'll see how things goes. So we are part of the consortium with the ICCAE. Professor Yingli Tian and Professor Hao Tang are with me today. So with this, Teddy, the floor is yours.
Okay. Okay. So I'm going to talk to you about semantically guided collaborative navigation, mapping, planning, and control for manned and unmanned platforms. But in between that, Zhigang asked me to also talk a little bit about my career. I'm going to start off by telling you a little bit about where I work, then my career, just one slide, and then some historical projects, which I thought you might find interesting. And a number of these would be have been of interest to also the intelligence community. And then will be the main topic, semantically guided collaborative navigation, mapping, planning, and control. So I work at SRI. SRI creates world-changing solutions to make people safer, healthier, and more productive. And SRI has done lots of famous things, like, for instance, we developed Siri, which then Apple bought, and that's why you have Siri. Or here in the Princeton office, we developed video insertion for a company called Princeton Video Imaging, which was spun out by an ex-vice president from our research lab over here. And that led to the 10-yard line in football. So you've watched football and you've seen the yellow 10-yard line that was created by PBI. And the first system for video insertion was done by us in our lab here. I'll tell you more about it. Or we developed Nuance. And recently Microsoft bought Nuance. This is for natural speech recognition. So SRI was founded in 1946 by Stanford University. It has about 1,500 staff members, and we do about $500 million of revenue. And we are a nonprofit. So we're not like a university, and we're not like a company. We are a nonprofit research place. And we do a lot of work for the federal government, from DARPA, Department of Defense, and Department of Homeland Security, intelligence communities, Department of Commerce, etc. And so we do a lot of our invention out of these different government projects. But then we also try and mature those technologies and transition them and apply them to various applications. And the way we transition technologies is, one way is, of course, we develop solutions for the government which get deployed, but then we also start up companies. Like I mentioned, Siri was a company we started up, which then Apple bought. So we are constantly creating new companies. And then we are also applying it to various different applications. So, this is like a loop. You invent, you transition, you come up with new app problems, you invent more, and you keep doing this. So SRI, Center for Vision Technologies, which I lead, has about 90 staff members, and it has a 40-year history in computer vision. I was telling you about insertion in TV games. That's the first actual real application of augmented reality. And the first time it was done was in 1994 for baseball games. And we actually inserted ads for the Baltimore Orioles game on April 1st. It was at the Orioles Stadium in Baltimore, and I was there, and we inserted it. Now, and then in the beginning, they were trying to make a business out of inserting ads for baseball games and things like that. But then later on, they switched to the 10-yard line in football. amongst other things. And we also developed a mosaicing thing. I'm going to tell you a little bit more about it. I'll also tell you a little bit more about video flashlights to give you a little background of the types of projects I've done in the past. We developed and this change detection technology, we also applied for breast cancer to compare MRIs taken at one time with an MRI taken another time to see if there was cancer. And this also has been deployed in many hospitals. So the SRI Center for Vision Technologies, which I lead, works on a number of areas. Like we work on computational sensing, how to see better. So for instance, we do projects for the Army when you're landing helicopters, how can the pilot see through all the smoke? Or for autonomous cars, how can you see when it's dusk and the sun is shining directly at the car? Then we do a lot of work on 2D, 3D reasoning for problems such as where am I, what is around me? And we've done a number of programs like that. Or we do programs in augmented reality. We developed a system for augmented reality binoculars, and I'll tell you about that in a second. We do a lot of work on collaborative autonomy, where one human is controlling lots of robots. And I'll tell you a little bit about what we're doing there. We do a lot of work on understanding humans. So a computer is watching humans with cameras and other sensors. We developed a system for Toyota for driver state monitoring, which has been deployed in their concept car. It does emotion detection and drowsy detection. We do a lot of work for the intelligence community on vision analytics, cloud-based processing, image search, social media analytics, activity understanding. And of course, nowadays, a lot of the work in computer vision and AI is all based on machine learning. So we do a lot of core machine learning work, which sort of is a foundation for all the other areas. So I'm going to tell you a little bit about these three projects, Video Brush, Video Flashlights, and augmented reality, and then we'll switch to the main topic. So, for one of the technologies we developed is what we call extended blended panoramas, where the need is to construct a very wide angle up to 360-degree panoramas of a scene. For instance, this is our library. It used to be a library here in our building in Princeton, New Jersey. And you can go around and take a lot of images, and we can automatically construct it like a spherical panorama, which you can then travel around and look at from different angles. So we created this, we got very excited about this technology in around 95, 96. And we created a company in 98 called Video Brush. And Video Brush was the name which my wife came up with. And the idea was to use the camera as a paintbrush. So here you can see, for instance, we are scanning a whiteboard going back and forth. And at that time, Toshiba had come up with a laptop. And we were very excited that we could do all this processing in real time on that laptop. So we developed this technology where you could scan a whiteboard by just using a laptop to scan it. And if you just did it naively, you would get what you see over here with my mouse. The image would be broken up. But by doing it well, you can get a really nice image which doesn't give you any seams or misalignments. And I remember flying to Toshiba in their office, US headquarters in Orange County, California, showing them a demo of this, and then getting a contract with them for being able to bundle the software with their laptop. And that's what launched this company, Video Brush. Unfortunately, it didn't succeed, but it did end up with Google. In 2011, we licensed it to Google, and it was part of all Android phones. So I'm going to, you can use this also to make nice panoramas, like this is of the Princeton Chapel, where you can scan multiple images and stitch them together and also make them blended so you don't have seams between them. Or we also did it for making aerial mosaics. And this was of a lot of interest to DoD and the intelligence communities at that time, because they have a plane flying by taking a lot of images, and we would automatically stitch it together and make a seamless image. So this was one technology which I developed at a transition. We started working on it in '95, and we did different types of transitions right to the government for commercial applications and all that. Another technology which we developed, there's a whole list of technologies over time. Another one I'm going to talk to you about is this thing called video flashlights. And this was a technology we developed around 2001. And in fact, 9/11 happened, and that had a lot of inspiration for us to develop this technology. And so what happens is, say you have a security guard at an airport, and like say Newark Airport, they may have 200 cameras in a terminal. So there are 200 cameras in a terminal, and the guard is looking at all of them, and it's very hard to figure out what's happening. So our idea was that we can take all the feeds from these cameras and stitch them together into a 3D model. And it's a live 3D model. So it's not a 3D model which is static. It's being overlaid with these videos from these cameras live. And then the guard can fly around with a virtual camera. He can, she can look at it from a bird's eye view and see everything, or can go up close and look at something. So we deployed this at multiple airports. We deployed it at Newark Airport. At Newark Airport, we deployed this at Terminal B. And we had two sets of cameras. We had cameras which were zoom cameras, which you could move around. And then we had wide angle cameras which covered the whole area. And this was used both by the security at Newark Airport for seeing if somebody was breaching, like sometimes people would open, passengers would open the gate and run into the tarmac or something like that. And of course, that's a security violation. So it was used by the security guards to understand if somebody had come into the grounds. And it was also used by the operator who would speak to the pilot after the plane landed to guide them to the gate. So here you can see a video of the system in operational at Newark Airport, where you can see in the middle is a pan tilt camera, so you can zoom in and look at something up close, like here's trying to look at who's driving this car or this pickup truck. But then you also have the wide angle view, which is telling you what's happening elsewhere, right? So you see both of them. Another airport we deployed it was Jacksonville Airport, where you can see that we can track someone right from there to the TSA checkpoint all the way to their gate, and we can see what they were doing. So after 9/11, for those of you who were older at that time, there used to be lots of times where the whole terminal had to be cleared because somebody had run through the X-ray checkpoint or something like that, and they were worried, so they'd have everyone come out and then everyone goes through the X-ray checkpoint again. With this, we could track everyone where they were, and so they could go and see, okay, this person ran through, but what did they do? And you didn't have to clear the whole thing. So this was a lot of fun to develop these kinds of systems, and we eventually sold this technology to a company called L3, and they won a big contract using this technology for modernizing training used by DoD. So the Marines would train the Marine Corps trains the Marines war fighters, and they would use the technology to be able to replace and get much better understanding of how the Marines were training. So a third technology which we developed recently, and we're still working on it, is a technology called augmented reality binoculars for training. And here the goal is we're developing binoculars for special forces, so for training, and also for tactical use, where you can see a soldiers looking at a scene with the binoculars, and what they're seeing through the binoculars is an augmented scene. What we are showing, so in the real scene, there's no tank out there, but in this augmented scene, when he looks at the binoculars, he sees a fake tank there. And then he or she can then use this to get their training. They can talk to a plane and say, okay, this is where the target is. And based on that, you can fly a synthetic plane and you can practice throwing a bomb on this target. And if they were off, then they can tell them you were off a little bit. So it saves them a lot of cost for training, because otherwise they got to put real targets and have real planes fly, and those are very expensive. So we developed augmented reality binoculars, which are the first kind ever. There's no augmented reality binoculars before. And it was a very nice application. And it has a lot of commercial use too. I'm a bird watcher, I go birding, and it would be really cool to be able to put up these glasses and binocs when you're looking for birds, and it automatically tells you what you're looking at, or helps you find the bird based on the sound. I'll show you a video of this for the training app. So now you should be, you'll hear some sound and video. On this left screen, you'll see the normal view, and on the right over here, the circular kind of display, you'll see the binocular view. And they're both being shown simultaneously. So you'll see this is a synthetic target we placed here, and there'll be a synthetic helicopter, but there's rail traffic in the scene. This is looking at Route 1 from our building. So that was an application which we developed, and actually we are still working on that today. So this is a background on some of the projects which I have done in the past. And what's exciting about working in this field, because you have lots of applications. The very nice thing of working in computer vision and machine learning and AI is there are lots of applications in lots of areas. And even for intelligence applications, there'll be lots of different applications. So I've been, this is one slide on my career. I'll just go bottom up. I did my Bachelor of Engineering from IIT Kanpur. Then I did an MS in Electrical Engineering from State University of New York in Buffalo, and a PhD from UMass. I worked in IBM for a brief period, and then I've been at SRI, Sanofi Corporation. Sanofi Corporation was acquired by SRI in 1987. It used to be the RCA Research Labs. So I've been here, basically worked for the same company from 93. Now it's about almost 28 years now, and I've just risen through the ranks. So that was a brief of my career. And as I showed you on those applications, which I did, it's exciting to work in this field because of all the different areas that you can work in. And also because you're trying to understand how to make an artificial system, which eventually, hopefully, can be as smart as humans. And so it's both intellectually very understanding, and also you have lots of applications. As they say, about 50% of our brain is being vision, right? Okay, so now I'm going to get to the main topic, where I'm going to talk about robot autonomy. And I'll also talk about in it different applications for intelligence. So for a robot to move and go from place to place, it has to solve 4 problems. It needs to solve the state estimation, be able to know where am I. It wants to know what is around me, so we call that mapping. What's around me, and not only is 3D map, but what's around. Then if I want to go to some place, how do I get there? And then what actions do I have to take? So one way to do navigation is to build maps. And you can do these on the fly. So this is our building in Princeton, New Jersey. And this is a colleague of mine walking from outside to inside the building. And this is the path which he took. When he's outside and in the open, then he can locate, you can locate him just based on GPS. But when the person goes under trees or goes into the building, GPS is no good. Or when he's very close to the building, GPS is no good. So there we rely on other sensors such as IMU, inertial measurement units, cameras, micrometers, barometers, ranging radio, besides GPS. And then we create a map on the fly as you're walking. And then we match to this map the next time you go, and then we can keep building up the map. So this was the sort of, you see these dots, blue, green, yellow. These are based on height above ground. And these are little points, 3D points in the scene, which have been recovered as the person walks. And then as the next person walks, they can use these as landmarks to locate themselves. Their system can use these as landmarks to locate themselves. And as they take a different path, it keeps updating the map along the different path. And that's what you see over here. And so you can see they climbed upstairs, they went to our coffee room, and it's going to build us both a three-dimensional map based on where they went and combine it with the previous map. And that's what you see over here. This is the combined map with two people's walks. Then a third person may go, and when they walked a common area, it would use those landmarks, and they took a different path to get there, it would then extend it. And then you can build a complete 3D model like this. This is a point cloud model, which is showing different features which have been detected in their locations. So it's on the fly creation of visual maps and then matching to these for subsequent runs. And we have a system called CAMSLAM, which does this, which combines visual inertial odometry with an error state Kalman filter and mapping, and they both work hand in hand. So this is an application of it at a warehouse. So this is a drone, and this is a warehouse, and the drone is being used to monitor the what all is there in the shelves. So you can see this is a 3D point cloud we built of the drone, and as the drone flies, you will be able to see it going through this model where it is. So you can see this little blue dot when my mouse is showing how the drone is moving. The drone is basically using this 3D point cloud to locate itself, and it's also updating it, and then it's navigating down and systematically scanning the site. Right? We also use this system to in warehouses for moving tractors and things like that. Another application of this is for autonomous cars, where this is driving through Princeton, and I'm matching to a previous time when I've driven through it. So I've driven through it, and I'm matching landmarks from one time to a previous time. And then using that, I can locate the vehicle. So this is driving from our campus through downtown Princeton, and we can locate ourselves by using these pre-mapped landmarks. Right? Now, one of the challenges with this technique, of course, is when you're driving, if you see the landmark matching, let me pause it, it's matching to things, cars over here, it's matching to things on the tree. And if you go in the summer, these trees may have leaves on it, so it's not a good landmark. Or if you're matching to things on cars, the cars may not be there the next time you drive, right? So that's the weakness of this kind of approach. So what we developed next is something where we're using more AI, is what we call semantic inference, where what we're doing is we're actually recognizing things on the scene and labeling them and using that to know where you are, to help it know where you are. And the sharing semantic information is also very useful for for collaboration. So for instance, if I'm giving my wife direction about where to go, I'll tell her, go straight, turn right at the gas station, go to the Dunkin' Donuts, and the shop is right opposite Dunkin' Donuts. So it's basically a lot of semantic information. And so if the computer can recognize that same semantic information, it's much more efficient to communicate it that way. And that's what you see over here too. This person sitting on this wheelchair is just telling the robotic wheelchair, go to the kitchen that's down the hallway, and the system should be able to understand that. So the first way we use semantic inference, here we are driving down Princeton. If you're used to Princeton, this is in Palmer Square, and we are labeling everything in the scene. We're labeling it as sky, building, road, pavement, signs, fence, things like that. And the simplest thing we can do for navigation is saying, don't use any landmarks which are on things which change. So don't use any landmarks which are on vehicles, on trees, on people, because they won't be there the next time. Use landmarks which are more permanent, like things on buildings, road markings, things like that. And if we do that, then we found we can improve our performance by 8 to 20%. And so that was the first way in which we use semantics for navigation. And the key technology required here was being able to do this semantic segmentation. But this general problem where you have lots of images and you want to locate yourself from a new image is a very useful problem. Not just be for autonomous cars, it's actually an intelligence problem, because intelligence agent given an image will want to know where was this image taken. So the problem is, given a set of monocular images for which you know their positions, you want to geotag a new image by matching to this database. And this should be in the presence of large changes across weather, occlusion, illumination. So, you're trying to match this image to images taken in the past, and there could be weather difference, there could be season difference, there could be occlusions, like there's a big truck blocking half of this image, it could be day versus night and all. And it's a big data problem, because if you represented the world as lots of images, there could be a lot of images. So it's a huge number of images to search through. And the idea how you solve this technique is by basically building these feature representations. So given the database of images, you generate a representation for each image. And then given the query image, you also generate an image representation, and then you do a search based on this representation, and you get candidates. Very similar to how when you do your Google search, you type in a few keywords and Google gives you candidates. And so similarly here, given the database of images, you've come up with a feature representation, and given a query, you generate a feature representation, you come up with a list of candidates, and then you can do some refinement and say this is the best second and third. So this is a problem called visual place recognition, and it's a big problem in computer vision. And of course, the challenge in this case we're trying to do is be robust to all these things, like weather, season, occlusions, day, night, etc. And one way in which you do this, this feature representation which we have over here, we take these images and run it through some neural network. So here I'm showing you an example from face recognition, where we have many images of Steph Curry, who's one of my heroes. And with Steph Curry, we're running it through a CNN, and a neural engine, and it's coming up with some kind of feature representation. And we also have Klay Thompson, and it's also coming out with feature representation. What we want to do is all the representations for Steph Curry, we want them to be close in this space, in this embedding space, and we want the image for Klay Thompson to be far from these. So you want to come up with some kind of neural representation which puts all images of Steph Curry close and puts all images of Klay Thompson far from that. So when you're given a new image of Steph Curry, you can immediately say it's the image of Steph Curry and not Klay Thompson. So similarly, and you minimize this by something called a triplet loss, where you use these three images, the anchor image, a positive example, a negative example, and you use that to train this neural network to this embedding space. So we want to do the same thing here. We want to come up with some kind of image representation which puts all the images of the same place taken at different times, different seasons, day and night, close by, and images are different. So then you can retrieve it very easily. So then the challenge is, how do you come up with this image representation? And another big challenge when you work on AI is collecting training data. Right? In fact, there's a whole industry now of people annotating data for different AI problems. So we had a brainwave when we were thinking about this problem, and we were thinking, there are lots of webcams all over the world which are operating 365 days a year and day and night. So they're operating 24 hours during all seasons, all weather. And so we collected more than 2 million images from 2,685 static webcams. And we got this data. And then we said, okay, the data from any webcam, the feature representation should be close together across all these different changes and far from the others. Right? And so we train a system to come up with this embedding, which does this. And how we do that is by essentially using semantics, just the same semantics which I showed you before, where we were taking the image and breaking it up, saying this is tree, this is road, this is pavement, this is building, this is car, things like that. And we also train the neural network to pay attention. I'll explain that a little bit more in the next slide. But let me show you this video first. So this is the video of driving through a city in Europe, and this is in summer and winter. So in the summer, you see green grass, some grass on the pavement, leaves on the trees. In the winter, you see snow. But you can see on the right-hand side of the semantic segmentation, and that looks, you'll see it looks pretty similar across both of them. Right. And so given this, what we do is train a system to use both the original images and the semantic images to be able to learn to derive features from these two. And it also learns what to pay attention to. So if you remember in the first example I told you, we told the system to ignore features on people, on cars, on trees, because they change. Here, instead of us telling the computer what to pay attention to, it automatically learns itself. It automatically learns this is what I should pay attention to for this kind of image, and this is what I should not pay attention to. And so we feed the system using both the RGB and semantics and this attention-based feature network to come up with these feature representations. And then we use that same triplet kind of loss, which I was telling you, to minimize its neural network. So this is an example where we built a database of images of the city in the winter, and now we're driving through the summer. And every time this image matches, we show the top 4 matches from this database. And every time it matches something and the match is within 6 meters of this image, we put a green box around it. And so you can see we are able to do pretty well. We are driving in the summer and matching to winter images. And mostly for all of them, all the summer images, we're able to find the right set of winter images. And I'll just pause it at one of them and you can see that, right? So we're able to do it. It's quite different lighting. There's snow over here, there's no snow over here, things like that. There's leaves here, there are no leaves here, but still we're able to match these quite well. This technique also worked amazingly even when we went from built the database at nighttime, and now we are matching to a video taken at daytime. And that's kind of amazing because even for humans, this can be quite hard to match an image at nighttime to one taken at daytime. And you can see that over here. Okay, so that was a nice example, and we're using semantic reasoning to know where you are. The The next problem we worked on, by the way, I can take some questions relevant right now, or we can wait till the end. What would you like? Because I'm going to start the next part.
Tell how much time you have?
I have about another 10 minutes.
10 minutes, maybe let's finish up with it. We have quite some questions, you know.
Okay, so
I'll ask the questions, you will end up, you know, everything.
Okay,
I'll let you finish after everything.
Okay, great. So, so in the previous example, I showed you how you can find images from a database of images, but there were images on the ground taken with images on the ground, only taken at different times of the year or different times of the day. But often you may not have images on the ground. And if you're, for instance, if you're building autonomous cars, it's much easier to build a model from the air. It's much easier to have a city, a helicopter fly over a city, or a plane fly over a city, or a county, and build a model of it, than to drive through every road in that place. So the next thing which we worked on, and we're still working on, is how to match ground images to aerial reference, right? And the aerial reference could be just overhead imagery. It could be digital elevation models, DEM. It could be LiDAR. And from that, we can extract semantic labels. We can extract skylines, spatial signatures, textual signatures, building signatures. And then we can match features from query images to this database to know where this image was taken from. So I'll show you two different ways in which we've done this. One is based on skylines, and the other is based on semantics. And this is a way, method based on skyline. So given an image, like you see over here, we automatically do the semantic segmentation, and we're able to recover which parts of the image are sky and which parts of the image are not sky. We run it through this neural network, and using this neural network, it's basically taking the image over here on the left-hand side, and it's producing the segmentation mask on the left, on the right-hand side. And then with that, we are able to say this part of the image is sky and this part of the image is non-sky. And then we can detect the boundary. And we can also do that for the reference image, right? So we can also do that for the reference database. And then we can render the reference database from different viewpoints and then match the video to that. And that's what you're seeing over here. You're going to see in this video where I'm driving through Princeton, and you can see it matching to the skyline visible at Princeton from the 3D model. And you can also see us driving in a rural area, and it's matching to the skyline out there. So in Princeton, of course, the skyline is mostly buildings and trees. Rural area is more trees than buildings. But you can see both of them. What you see is the video over here in the middle, and then you see the reference rendered in a wide field of view on the bottom. And as you drive, it's rendering it, and you're matching to it. You can see that in all these videos. So you can see, and it's actually estimating the heading, and it's always doing a correction to the heading. I think white is a prediction, blue is the match of where the heading should be, and it's using that to correct the heading. So that's one method. The second method which we did was we took LiDAR, and we now render it, and then we match the ground image to the LiDAR. And here we're doing semantic segmentation. We're doing semantic segmentation both of the image and also of the LiDAR. And then we're doing the same embedding which I was talking about. We're putting the images and this LiDAR into this embedding space, and then learning how to put them together, and then using that with the matching. So this concept of embedding in AI is very powerful. It allows you to tie in lots of different information. Here I'm showing how I'm tying an image and LiDAR. We've also tied in image and text. You can tie in all different types of information into the same space, and then use one to reason about the other. And you can see matching the image to the LiDAR, and you can see that over here. As a person's walking, the images are being rendered to the LiDAR being rendered, and the images are being matched to it. And that's used to guide the system in knowing where exactly the person is. Okay, so these were, up to now, I've spoken about where am I and what is around me. Now I'm going to speak about these two topics. How do I get there? What actions do I have to take? So in these two examples which I was talking about, we were building a map beforehand. The map could be from the ground by driving before, like Google does or Waymo does. Waymo drives around these cities and builds maps, and then the autonomous cars use those maps. Or it could be from the air, like I showed you last. But there are lots of places where we want robots to go where there may not be a map. Say I haven't been to Zigang's house, but say if Zigang invites me to his house and I have to go to his kitchen, I'll be able to figure out how to get to his kitchen, because I know how to explore the house and say, okay, I know when I'm in the kitchen, because all kitchens are similar and I'm able to recognize them. So we as humans can navigate to in lots of places which we've never been before. So we should be able to train a robot to be able to do that too. And so here what we are doing is we're using AI-enabled autonomy, where we're using deep reinforcement learning, how to teach a robot to navigate by directly mapping from its situation sensors what to do next. So it's basically learning how, given an image, how what it should do next when it wants to explore that environment and go from one place to another place. And this kind of learning you can do on a simulator for lots and lots of cases. And once you do that for lots and lots of cases, then you can teach the robot how to go to new spaces, right? So this kind of deep reinforcement learning has been made famous recently by companies like DeepMind. They developed all these systems like AlphaGo and things like that, which use reinforcement learning to be able to play games. And people have been using these kind of techniques also to develop autonomous cars, robots, things like that. And you typically train them on a simulator, and then you transfer it to the real system. Deep reinforcement learning is better than traditional methods, but it requires lots of data. So this graph is showing, a traditional method would be SLAM, like kinds of techniques I showed you earlier, and you can get a certain performance. This is, SPL is what's the best route you could get. The best route would be 1, and with SLAM you can get to about 0.6 in terms of the shortest route you took to get to a place. While with deep reinforcement learning, if you train it a lot, you can start getting much better performance. And there was a paper in 2019 from Wichmans and all, they're from Facebook AI, where they claimed they've solved this problem, where after about 2.5 billion steps of training, essentially equal to 80 years of human experience, they found the system could be able to do this almost perfectly. But it needs a lot of training, as you can see in this graph. So our idea was maybe we can make this system more efficient by giving it semantics. So the semantics which I showed you earlier, where we were looking at a scene and recognizing tree, road, pavement, you can use that to recognize what's in the scene. And maybe the AI system can reason about the semantics to be able to do that. And also we built an occupancy map based on semantics to say, okay, this part of the scene is floor, this part is wall, this is door, this is chair, things like that. So here we are teaching the agent how to navigate in the simulated scene based on the semantic and occupancy map. We also found that we can improve this by giving it attention. So again, if you remember earlier, I talked about attention, where we were, instead of us telling the system what to pay attention to, it was automatically learning it. And here also, we taught the system how to pay attention. So for instance, when it's exploring a new environment, it'll learn how to pay attention to doors, because it knows when it wants to go from one locale to another locale, a door is a good way. Or if it's a drone, a window might be also a good way. Or it may want to pay attention to corridors, because it knows corridors leads to many doors. So like that, the system learns how to pay attention to different things, and it can navigate. And we found that by using the semantics and attention, we can do the same training used by the state-of-the-art system with less than 20% data of what they required. So it was like a big improvement on the amount of time it would take to train the system. And this is showing the system navigating. This is a state-of-the-art system on the top, and on the bottom is our system. And it is, we've asked it to go to a certain location, and you can see it'll get to it very quickly, while the one on the top is going to have to explore a lot more to be able to find its location. Okay, so that was all the things I wanted to talk about. I gave you talked about SRI and Center of Technologies, some of my historical projects and actually current projects, and this main topic on semantically guided collaborative navigation, mapping, planning, and control. So I'm ready to take any questions.
Thank you, Teddy, for the very informative and exciting talk. So we're going to have questions, number of questions, I think 15 questions. So we probably want to do it in 15, 20 minutes. Whoever, you need to go earlier, feel free to do that. So we're going to hang around a little bit for the questions. Ms. Jin Chen is going to moderate the question session. Jin, could you share your?
Yeah, I'll share the screen. So Dr. Kumar, can you see it? So I will read it. So the first question will be how the government's need identified, and does the government approach SRI with its need, or does the SRI approach with the government with the possibility as a new technology emerge?
I think it happens both ways. We come up with interesting ideas. We do internal research and development, or based on earlier research, or based on what's happening in the field. We come up with ideas, and then we go to the government and say, look, we have this new idea, this new technology which we are developing, and it can solve this particular problem for you. And then when the government might be interested in that, and then they will develop a project around it. And then many times the government, like we often work with DARPA or IARPA, Intelligence Advantages. Many times they are the program managers there is trying to identify, comes up with problems, and then we propose solutions to them. So both ways happen, and the best, of course, is if you can come up with an idea, then go to the program manager in DARPA, IARPA, or some other place, and tell them about it, and then they'll start a whole program based on it. Then you have an advantage of winning that, because all these programs you win by competition. None of this work which we do is sole source. We are always competing for it with everyone else, with universities, with other companies. So it's you survive by your wits.
Yep.
It's very honest work. You have to do well to survive. Yeah.
Great to know. So let's go to the next question. Are your project driven by the SRI research and development object, or is more required by the client?
Well, SRI is a research and development place, so there isn't like something like the company is doing research and development. There are different groups. We don't normally sell products. We do sell a few, but not too many. So most of our objectives are either developed, just like Zhigang, being a faculty member, has research objectives of his own. So some of the individual researchers are team research objectives, and some are coming from the client. So it's very similar answer to as question one. It's both ways.
Great to know that. And what type of preparation should be taken for the student if they want to get a chance into the intelligent analyze?
I would say it depends what you want to do. It's a very big topic. There are lots of areas. It's an exciting topic. I was telling you about one kind of problem we've been working on, which is given an image, where is this image taken from? This is a problem of great interest to intelligence, but also typical intelligence problems is there's a lot of data and it's like searching for a needle in a haystack. There's a lot of confusion, a lot of noise, and how do you figure out what's happening? Yeah. And so it's literally searching for a needle in a haystack. AI and data mining, data sciences are key technologies for intelligence, but so are how do you collect the data, right? And there are many different careers you can have in intelligence analysis. If you wanted to do the stuff which I do, then of course doing computer science, electrical engineering, AI, machine learning, those are the kinds of things which I would do and study.
Great. And then what is the story behind that's critical for how your career start?
Well, for me, ever since I was a little kid, I always liked solving puzzles. And I also, whenever I ask people, when I was younger, I used to ask people, if you have a grandkid, what is the most important quality you would like your grandkid to have? And most people would answer the question, they'd want their children to have integrity, which is a very good answer. You want your children to have honesty and integrity. But a thing which has always been also important for me is a sense of wonder. Mm. So I've always been, I always like learning how things work and understanding them, and sense of wonder. And that has always motivated me. And that led me to have a life as a researcher, a career.
Right. Mm-hmm. So the next question is, this car recognition the same type of technology that can recognize people in the photo?
Yeah, I showed you earlier a picture of fine-grained recognition of vehicles where, I don't know if that's the one you're referring to, where we were showing it's a Honda Civic 2011, things like that. So it's similar technology to the one in photos, but you are trying to, when we were trying to do car recognition, we were also trying to recognize the parts of the car and use that to distinguish one car to another.
Great. And next one is the video flashing system similar to the Google Street View, and what is the basis of the technology?
So video flashlights is not similar to Google Street View. Video flashlights, we are combining lots of videos onto one 3D model, and then you can fly around and look at it, and it's being done in real time. The key technology here is the idea to be able to align videos from both moving and fixed cameras to a 3D model, and then use that video to texture the 3D model and then see it from different viewpoints.
Right. And next one, the challenge with the deep reinforcement learning approach to navigation is that they are black box, and how would you work in to make those systems explainable?
That's a very good question. So I think one of the ways we are doing that is by bringing in semantics into the scene. So then you can use that to ask the user, the system, you can query it to ask the system what happens. You can explain in semantic terms why it was saying what it did. The other kind of analysis we've done for explainable for AI systems is to also use attention to say what does the system pay attention to. And when we derive automatic attention maps, you can see those attention maps and saying, okay, this time, this is what it was attending to. And the third kind of work which we've been doing to make these systems explainable is what we call counterfactual reasoning. So you're seeing something in the scene, and the system is making a decision, Now what we do is we go and remove that from the scene. And then we run the system again and we say, what decision did it make? So this counterfactual reasoning also helps us do that.
Great. And next one, where did you see the human hand of the bulk of the work within the intelligent process? And how would you apply this concept to collection management and targeting?
So as I was saying earlier, a lot of intelligence work is searching for a needle in the haystack. And so there's a big haystack to search through. And so how to organize the haystack, how to be able to partition it in different ways and things like that is a key thing. And how would you apply this concept of collection management and targeting? So really, so one way in which you do targeting, for instance, is by matching images to reference data. Or to make a decision, you're trying to decide if something is a target or not, and you looked at it from one view, how can you look at it from another view to decide if it's a target? So all of this can be done easily by learning beforehand through simulators and previous data, what's the best angle to recognize this? So given this angle, it can say, okay, I can't tell for sure whether this is a truck or a van, but if I go and look at it from this view, I'll be able to tell much better. So if you train the system to be able to do these tasks beforehand, you can automatically learn what to do next.
Okay. So let's go. Next one is, what's the current expectation that the intelligent community have for the AI in terms of improving the intelligent community or its better use in the future?
AI is a very hot topic for the intelligence community. In fact, it's a very hot topic for the US government. They have, it's a national technology priority. And, President Biden has also spoken about it. So there's a lot of funding for AI by the intelligence community, and they see it as a very important thing for US to maintain leadership. And it's a key technology for us, I think, for the needle in the haystack, to make sense of the haystack here.
Yeah, great. And how long on average does it take to develop a new technology?
It depends. The biggest challenge in developing AI systems, a lot of the AI systems which are there right now, which are working well right now, have a lot of supervised training. So you have to collect a lot of ground truth data and annotate it, and that takes a long time. And it also takes a long time to train the system, right?
Yep.
So you need powerful computers to train it, and then you need to collect the data, the annotated data, and then depending on your application, that can take a long time. So there's where the forefront of research nowadays is, how can you automate the learning? How can you do learning without, you can do unsupervised learning or self-supervised learning. So there's a very famous system which was developed last year called GPT-3, which is used for natural language understanding, which does, there's no, you don't need to provide it any labeled data. It just reads all the text, and it does its learning by trying to predict the next word or the next sentence. It'll read a sentence and try to predict the next sentence. And they basically read the whole web and all the books and anything which is digitized, and it can do amazing stuff. But that's where the forefront is, how to learn without having to do a lot of supervised training. But what is deployed right now mostly is what is supervised training. And so how to collect the data for that is a big challenge.
Got it. And how does an IMU function? What's the underlying technology?
So an IMU has two parts to it. One is an accelerometer and the other is a gyro. So with the accelerometer and the gyro, you can measure both how the velocity and acceleration is changing, and with the gyro, you can also measure how it's rotating in all 3 dimensions, and with the accelerometer, how it's moving in 3D space. So an IMU is giving you 6 measurements. The how it's translating in 3D space and how it's rotating in 3D space based on these measurements. And it also tells you your angle with respect to gravity.
Mm-hmm. So next question is, how does the daylight also affect the recognition?
So daylight affects recognition because it changes based on, things can look very different. The best time to take pictures is the golden hour. I don't know if folks know, the golden hour is 1 hour after dawn and 1 hour before sunset. If you want to take nice scenic pictures, go take a walk during the golden hour. So things look very different, as you know, from the morning to the evening to full noon and things like that. And so the appearance changes, shadow changes. So you have to be robust to all those things.
Great to know that. And does adding some method to detect the affine transformation help to dealing with different angle of the similar image?
That's right. When you're training the system, so remember, I was telling you about the triplet loss and telling you when given image, you take all the other images of the same thing, say of Steph Curry under different times and put them together on this location, and in the embedding, you want them to be close. So one of the things which you do when you're training these systems is also do affine transforms to them. And then you use that to augment the training. And that will help you too, yes. Great.
And do you have any recommendation for any resource where we can learn the basics of this?
Well, by basics, you're talking of AI, deep learning, and things like that.
Yep.
So, I mean, nowadays it's amazing. Everything is on the web. The whole world is accessible to you on the web. I did a Coursera course from Andrew Ng. It's a great thing. But all the lectures from all the universities are also on the web. They're great lectures. I don't know if Zigang's lectures are on the web or not, but lots of university professors' lectures are on the web. You can learn from those. I like the lectures from Stanford University professors. They're very well taught. But there are many professors' lectures are on the web. The other nice thing is when you're reading papers nowadays, when I was a graduate student, when I was reading papers, we had to have all these big, thick conference volumes. And then you would find a paper there, then you would search, okay, I want to read the paper from CVPR from this year. You got to find somebody who has that volume. If you don't have it, photocopy the paper or write to the author to mail you the paper. Nowadays, everything's on the web. It's very easy. Everything is an ArcXIV. So you read a paper, there's a reference there, you can look up the reference. The whole world's available to you on the web nowadays. It's so easy. And a lot of the lectures are also on YouTube. You can also listen to it. And the nice thing of listening to lectures on YouTube is, you can go back and rehear something that you didn't understand and things like that.
Right. And next one, did you ever go outside of the virtual spectrum in this system? Future matching with the pyramid, for example, might get in the base of the tree, which is unlikely to change, and the radar might change a different and a better future than the visualized future.
We have used this embedding technique for matching all kinds of sensors. We've used it for matching radar to images, LiDAR to images, text to images, you can match radar to LiDAR. And we've also developed techniques not based on machine learning also to do it. But yes, we have.
I think the question they also have that the thermal, is thermal a better way? You say that's more stable, or is it still not?
Thermal has its own challenges. It's very nice for detecting people and things like that. But there are days when you're out with a thermal camera where you don't see any gradients at all. And there are days where it really differentiates things. So it's not like thermal. Ideal system which we have has both regular cameras, thermal cameras, multispectral cameras. The more information your application allows you to use, the better off you are.
Great. And next one was the most important training for an undergrad student and then a graduate student to work in this field.
I think if you're interested in AI, machine learning and all, of course, you should learn the fundamentals. You should know maths, up to linear algebra, calculus, things like that. You don't need very high maths, but you need to know linear algebra and calculus, matrices, things like that, optimization, but then also programming. And really, the best way you learn something, there are two ways you can really learn something. One way you learn something is by actually trying to implement it yourself. So if you implement yourself, you learn a lot more. And the other best way is to teach someone else. Also, if you form a group of other students, you teach each other. Or you teach someone else. You really know if you understand something well, if you can explain it to someone else.
Yeah, this is how I learn things. I learn from students. By
Yes.
teaching students, actually I learn from them.
Yeah.
Yeah, that's great. And I know you kind of mentioned the math and the programming skill, but which one you think would be more important? The math skill, programming skill, critical thinking, or the communication skill?
I would say the most important is none of them. The most important is if you have a sense of wonder and you don't, if you have a bad day, you're going to sleep, you wake up the next day, it's a fresh start.
Right.
So if you have a positive attitude and a can-do attitude, all of these will go to this.
Great. And what do you think are the qualifications to work on the project for the defense, security, and the intelligent applications?
I would say there are lots of different things you can do in these applications. You can write new code. So for that, you need to learn math and programming and all that. You can be doing program management. You can be doing testing. You can be developing concepts on how they'll be used. You can be finding customers for it. So there's a wide variety of qualifications that applications have. It's like working for a company, you know. You can be on the customer side of it, on the technology development side of it, on the testing side of it. There are lots of different skills which they require.
Got it. And what is the best way you have found to really learn a new subject well?
Listen to a few good lectures from people to understand what's important, and then try and read some papers and talk to people and work on it actively. As we said before, try and use what you're learning. Don't just read it, try and use it and try and explain it to someone else, teach someone else.
Got it. And do you have a preferred resource for learning about the matrix map based on the navigation system?
Well, the best textbook when I was growing up was the one I liked the most was Bertolt Hahn's textbook on robot vision. It's a good fundamental book. There's a nice textbook by Zaleski, who's done a lot of work on metric map based stuff. And after that, a lot of the latest stuff, Zaleski's book is a little bit more up to date, but Hahn's, there's also a book by Zisserman and Hartley, I think, which is a very good book. But after that, you have to rely on the latest stuff, on papers and these lectures which are being taught in courses. All these Coursera classes, like Andrewing classes, are really good.
Yeah, great. And I think that's it for all our questions. And there was a comment said this speech is very well informed and we learned a lot from you. I really appreciate it.
Thank you so much.
Thank you, Jim. Thank you, Teddy. So they got a lot of feedback here. They say all the good things to you. Thank you, Teddy, for all. We should have done this more often, right? So fortunately, I'm going to share one slide. You guys just hold on a little bit for the coming up lectures. You will see that we now have like 3 more line up. Every month we are going to have one. We already confirmed the one date is June 15th. It's a Tuesday. During the summer, we're going to do it in the middle, either Tuesday or Wednesday. So you guys want to go away, right? So I still hope the students who, I know some students, you are in my class, you are not going to be in my class in the next semester, but they come back, okay? We're going to have Eric Blatt from the Air Force Research Lab at AFOSA, Air Force Office of Scientific Research, from the government side, okay, to talking about the story of defense security. And there's Steve And Tao Wang is actually was my PhD student. They work on in the defense company BAE in Boston. And then Daniel is going to come probably in the summer, end of the summer or early fall. So with this, we have more lineup. Maybe have 2 more, maybe more. So we'll see how things goes. Thank you. So today we have like 80 people in the peak. Okay, so it's a very good turnout, and we hope you guys come back for the next one. All right. Thank you, Teddy.
Bye bye.
Okay, bye bye.